Hi guys, welcome to this page of the notes, and what we're going to do here is one more problem where we're going to go ahead and graph a logarithmic function that has some transformations in it. So let's go ahead and start there by figuring out what is our a, our h, and our k. Remember, the general formula for transformations is going to be f of x is equal to a log, whatever the base is, of x plus or minus h plus or minus k. So here we go. We go ahead and take a look at this. If I have an a, it'll be out front of the logarithm. There's my log. I have a 1/2 out front, so that means that a is going to be 1/2. Now, because a is positive, it's not going to be a reflection across the x-axis. But because a is a fraction, remember, anytime a is less than 1, it's going to be a vertical compression. All right, so we'll have a vertical compression in this case. If I have an h, it'll be inside parentheses along with the x, and I do have parentheses, so it looks like my h is going to be a positive 1. But remember, h is the opposite, so what this is going to do is it's going to shift the whole thing in the negative direction 1 unit. Here's what that means. My vertical asymptote is, without transformations, the y-axis. But the whole thing is getting shifted in the negative direction 1 unit thanks to h. So that means that my vertical asymptote is now going to be right here at x equals -1. Because, right, the h is going to shift my whole logarithmic graph to the left 1 unit, right? Because it's the opposite of h. Since h is a positive 1, I'll go to -1. I'll go the opposite direction 1. And so my vertical asymptote, which was the y-axis, now gets shifted to, sorry, I put an x, to y equals -1. Nope, I was right. X equals -1. Okay, k. If I have a k, it'll be tacked on the end, and I don't. So that means that k is equal to 0, and my graph isn't shifted up or down at all. Okay, so here we go. What we're going to do is we'll go ahead and set up our table, but this one's actually going to require a little bit of work up front. And here's the reason why. I said what you're going to want to do is we need at least 3 points, and those 3 points are going to be determined based on what the base of the logarithm is. So because my logarithm is a base 1/4, right, we said previously you want to take the inverse of that, which would be 4. Of course, we're going to want to do the log of any base is 1, and then we would want to do the log, since my base is 1/4, we'd also want to choose 1/4, because when the base and the augment are the same, they'll cancel each other out. But I have a problem. I don't just have an x in here. I have an x plus 1, and I have to do x plus 1 before I take the logarithm. So if I were to follow that rule we've been using, where I just simply take, right, my base is 1/4, I'll just take the inverse of that, which would be 4. Well, if I had a log base 1/4 of 4, I of course would get a -1, but that's not what I have. Please notice it's x plus 1. So if I just plug a 4 in here, 4 plus 1 would be 5, and I'd be taking log base 1/4 of 5, in which case I'm not going to get a -1, right? Log base 1/4 of 5 is going to be something else, some decimal. So here's where we're going to have to do a little bit of work up front. Here's what I know I need to get. Here's what I want. A little bit of side work. I know that I want my 3 points to be log base 1/4, right? Log base 1/4 of the inverse, which is 4, because that's going to get me a -1. And I know that I want to use log base 1/4 of 1, because log any base of 1 is going to get me 0. And I know that I want to do log base 1/4 of 1/4, because whenever the base and the augment are the same, they cancel each other out, and I'm going to get 1. But what I've got, right, is I've got an x plus 1 as my augment, right? Remember up here in my function, this guy right here, it's an x plus 1, not just an x. So here's where that little bit of extra work is going to come in. I need, do it in red, I need this whole guy, x plus 1 to be equal to what I want to take the augment, or what I want my augment to be, which is 4. Well, in order to do that, x needs to be equal to 3. So the very first data point I'm going to put in my table is actually going to be a 3. And here's the reason why. I go ahead and plug a 3 in here. Right? And what does that do? Well, 3 plus 1 is 4. Log base 1/4 of 4 is going to get me my minus 1. And then minus 1 times 1/2 is going to be a negative 1/2. Okay, let's keep going. Let's find the other one. I know that I want to take the log of 1. So I need this x plus 1 to be equal to 1. So what does x need to be? Well, subtract the 1 to the other side, and x needs to be 0. So that's going to be the next point I got to plug into my table. I'm going to put in a 0, because if I plug in a 0, then what I'll get is log base 1/4 of 0 plus 1, which will be 1. Log any base of 1 is 0. And 0 times 1/2 is just going to be a 0. So I now have the point 0, 0. And then we come back down here. Let's do a little bit more work. I know the next one I want is 1/4. So I need x plus 1 to be equal to 1/4. Go ahead and subtract the 1 to the other side. Get your common denominator. 1 minus 4 is a negative 3, so I need x to be a negative 3/4. So I come back up here to my table. The next one I'm going to plug in is a negative 3/4. And here's why. If I plug in a negative 3/4, minus 3/4 plus 1 is going to get me is going to get me 1/4. So negative 3/4 plus 1 is going to get me is going to get me 1/4, and then log 1/4 of 1/4. They'll cancel each other out. It'll leave you with just a 1, and you will get 1 times 1/2 is 1/2. All right, so again, in this one, when you do have an h, you're going to have to do a little bit of this side work down here to get those points that we want, which are the 4, the 1, and the 1/4, right, based on the base I've been given in this problem, which is 1/4. So here we go, back up here to the top. Oh, sorry, hold up 1 second. I apologize. There we go. We'll go ahead and graph these data points, and let's see what this comes out to be. I have 3 minus 0.5. Let's see, 1, 2, 3, negative 0.5. It's going to be, actually, here, let me do it in a different color. That guy right there. I have 0, 0 right there. Negative 3/4, 0.5, which is going to be somewhere right about there. Vertical asymptote is x equals negative 1. I come down through, connect all my dots with a smooth curve. Make sure you extend your line all the way through the coordinate point, or all the way through the coordinate plane, and put arrows on both ends, so I know you know that that guy just keeps going. And again, I've got my 3 data points. You must have at least 3 coordinate points, but we had to do a little bit of extra work to go ahead and get this one. It's not that big a deal. You just take whatever your augment is, whatever it is you're taking the logarithm of, and set it equal to what you want it to be to figure out what the x is. In this case, I set it equal to 0, I set it equal to 4, and I set x plus 1 equal to 1/4. That way I can figure out what x is going to get me that augment that I'm looking for. Again, if you wanted to, you could certainly graph the inverse, just switch the domain and range values, plot the points, and graph your exponential, or you could take your logarithmic function and do the 4 simple steps to find the inverse function. You could do either of those if you wanted to. One more quick point before we finish up logarithms, and I want to go back to a different, let me just jump back to one of these ones here. Here's a great exponential function right here, right? So I've got this exponential function here in red. Why do we like exponential functions so much? What we're going to do is we're going to see a number of example problems in later sections where we use a logarithm to model a natural phenomenon. Actually, we call them logarithmic scales. You probably have the most familiarity with it in chemistry when doing pHs, when you're calculating the pH of an acid or a base. You'll see that the formula for pH, for calculating pH, has a log in it. Here's the reason why. The reason we like logarithms so much, or we like to use a logarithmic scale, is for this reason. Please notice that as the values of x get really, really big, right? This value of x only goes to 10, right? My coordinate plane only goes to 10. But imagine that graph extending out to infinity. Look at how this logarithmic function kind of levels off as you get to larger and larger values of x. Here's what that does for us. Generally, when we're dealing with numbers, we like smaller, nice, neat numbers rather than gigantic big numbers. And sometimes what will happen when you're measuring the magnitude of an earthquake, or you're finding the ion concentration in an acid, right? You're going to be dealing with numbers that have to be in scientific notation. They're very, very big numbers. What we're going to do to make those numbers a little bit smaller, a little bit more manageable, is convert them to a logarithmic scale. And here's how it's going to work. Take, for example, log base 5 of x. And let's just do a couple of examples real quick for you down here. If I have log base 5 of x, and I choose a couple of x values. Let's say I pick really, really big values. I want x to be 100, x to be 1,000, x to be 10,000, x to be 100,000, and x to be 1,000,000. All right, here's what we're going to do. Let me grab a calculator real quick. Now, these are really big numbers. Yuck, 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 right? We'd like to avoid using those numbers if we can. Now, what I'm doing, right, is remember, my function, f of x, is a logarithm, right? So I'm finding f of x, which is equal to a log base 5 of x. In this case, base 5, that's just the example problem that I'm using. It's a log base 5. So here's what I'm going to do. I'm going to plug 100 in for x and do log base 5 of 100. So let me real quick do that for you. Find my change of base. We'll do log base 5 of 100. And what I get is a much smaller number than 100. I get 2.86, right? So instead of dealing with the number 100, I have the number 2.86. Yes, I realize it's a decimal, but it's a small number, right? It's this kind of nice, neat, small number rather than 100. It gets even better as I get to bigger numbers. Let's do it for 1,000. I get 4.29, right? Instead of having to deal with numbers that are really big in the thousands, I convert it to a logarithm, and I've got a number that's less than 5, right? 4.29 is a nice small number. Yes, it's a decimal, but it's still really small. Let's keep going. Even bigger numbers. Let's go to 10,000. I get 5.72, right? Now I'm dealing with numbers that are in the 10,000s. At this point, by the time you get to 10,000, trust me, you're going to convert it to scientific notation because these are really big numbers. But if I convert it to a logarithm, right, the logarithm changes it to a number that's much smaller, much more manageable. We can keep going. If I go on the x-axis all the way out to 100,000, check this out, I get 7.76. 0.15, right? When you're dealing with numbers in the hundreds of thousands, trust me, you're going to be using scientific notation. They're these gigantic big numbers that are kind of difficult to do calculations with because they're really big. No problem. We can get rid of the big numbers by converting it to a logarithmic scale where it is now a simple, smaller number, easier to work with. Would you rather work with something that's in the hundreds of thousands or work with 7.15? I agree, I'll take 7.15. Even though it's a decimal, it's easy to work with. Gets even better when I get to the millions, right? You are definitely in scientific notation area at this point. And look at this. You convert it to a logarithm, and it's 8.58, right? These are much, much easier numbers to work with. They're smaller, simpler numbers to work with than working with millions, hundreds of thousands, 10,000s, right? And so that's why we like to use logarithmic scales in the sciences, everything from physics to chemistry, right? We're going to use a logarithm to scale these numbers down. So when I get to really, really large values of x, as x goes to infinity, I convert it to a logarithm, and look, those y values stay down here in kind of real small, manageable numbers. If you consider what we just did, when x was equal to 1,000,000, right? When x was 1,000,000, look at where I was at. When x was 1,000,000, y is 8.58. So try to imagine that if you can. On this coordinate plane, you take that x value all the way out to 1,000,000. Even at 1,000,000, this red line is only going to be right about here on the y-axis, 8.58 or 8.85, whatever it was, right? It's a much, much more manageable number. And that's what we're going to do with logarithms. We'll take really big numbers, convert them to a logarithmic scale so that those really big numbers become much smaller, much more manageable numbers when you convert them to a logarithm. We'll get a lot more practice with that in later sections here in this chapter, but that's why exponentials and logarithms are so popular, and we really want to get a good grasp of how they work. They're going to show up all over the place. Guys, thanks so much for joining me for this set of notes. Hopefully you've got a really good grasp on both rewriting exponentials as logarithms and logarithms as exponentials using that good old snail method, and then of course graphing logarithms, which are just inverses of exponentials. I had a great time doing logarithms with you. I can't wait to see you in the next set of videos. I'll see you guys next time.